Hi everyone, good evening.
Good evening, sir.
Good evening everyone, good evening. How are you all today?
Fine, sir. How are you?
I'm good. Welcome all, welcome everyone.
Thanks, sir. How are you?
Hi, good evening, good evening. Welcome everyone, good evening. Hello, 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 welcome all. Okay, so I can see Dipin and Himanshi. Rest of the students have not switched on their camera, so that's not good, guys. I think you should switch on your cameras. And I can see the messages of Dipin, Nisha, Paul, Grace, Tasneem, Himanshi, Kirti. Good evening, everyone, and welcome to the session. Welcome back in the chapter Redox Reactions. We have seen first, in the first chapter, in the first lecture, I'm sorry, uh, we have seen redox reactions. What are the classical concepts of oxidation and reduction? What are the rules to find oxidation number? Then we practiced some of the oxidation number. Then we saw some fractional oxidations, which means sometimes we see oxidation number in fractions, but that is not the case. So that's what we have seen in the previous chapter, previous lecture. Types of redox reaction tak we have completed. Now today guys we will be starting balancing of the redox reaction, balancing your redox reaction by oxidation number method and ion exchange method. Okay, so today guys our main agenda, our main target will be how we can just balance the redox reactions. Okay, hi Jeevan, good evening. Hi Sudarshan, good evening. Okay, so today our main task, our main agenda is to learn how to balance a redox reaction, and that too by using two different methods. Okay, so see, I have already written everything on the notes. As you can see, balancing of the redox reaction can be done by two types. That is, number one is the oxidation number method, and number two is the half reaction method. So we can balance the redox reactions by two different methods: oxidation number method and half reaction method, that is also known as that is also known as ion exchange method, that is also known as ion exchange methods. So we will be learning how to balance these redox reactions. Okay, now if I talk about the methods, see, I have written everything in the slides. Okay, so whenever you feel that you want theoretical knowledge of any method, you can go through my notes. But trust me guys, all these things are actually not at all important for you. We actually don't require anything. I will, give you the example and you will get to know everything. Okay, so let's get started with the topic balancing of the redox reaction. I hope you all have mentioned the heading balancing of the redox reaction, and first we are doing it by oxidation number method. Oxidation number method. Oxidation number method. Now guys, see what happens is in the redox reactions, our chemical reaction takes place in two different mediums. Number one, acidic. Number two, basic. Okay. So what we do is, first let's see an example of a chemical reaction that is taking place in acidic medium. So Fe dipositive is reacting with Cr2O7 dinegative, and it is giving you Fe3 positive and Cr3 positive, and it is mentioned that this reaction is taking place in acidic medium. Okay, so now this is your question. So your chemical reaction is this, and this reaction is taking place in acidic medium. Now how we will be balancing this reaction? How we will be balancing such reactions? Okay, so now just observe the steps one by one closely. Step number one, please listen everyone. Step number one, write down all the oxidation number of all the elements. We do not require to write oxygen and hydrogen here. So first thing, iron. Guys, can you tell me what will be the oxidation number of iron here? Fe? What will be the oxidation? Yes, very good. So that's +2. Okay. What will be the oxidation number of chromium here? What will be the oxidation number of chromium here? Very good. That is +6. What will be the oxidation number of iron here? I can say +3, and that is also +3. So step number one is clear. Step number one is clear. Now step number two, let's find out which one is getting reduced and which one is getting oxidized. So guys, can you tell me what is the condition of iron? That iron, is it getting oxidized or is it getting reduced? Oxidized. Very good. Iron is getting oxidized because oxidation number of iron was initially +2, but now it is +3. So we will say oxidation of iron is taking place. Acha, by how many electrons, guys? 1 electron. 1 electron. So please mention 1 electron in the bracket. Okay, now what will be the condition of chromium? Reduction. Very good. And by how many electrons? 3 electrons. But this is the mistake we are doing. What mistake, sir? Actually, this chromium's oxidation number is 6 and this chromium's oxidation number is 3. So 3 electrons are accepted by one chromium atom, right? But actually on the reactant side, how many chromium atoms are there? 2. And on the product side? 1. So first, before saying this, we have to balance the chromium atoms. Let's add 2 here. Now 2 chromiums are here, 2 chromiums are here. Now if you say 1 chromium having oxidation number +6 and now that chromium is having oxidation number +3, which means 1 chromium atom is accepting 3 electrons. But in total, how many chromium atoms we have in reality? 2, right? So 1 electron, 1 chromium atom is taking 3 electrons. So 2 chromium atom will take in total 6 electrons. Very good. So we will be seeing actually the reduction is taking place by 6 electrons. Is it clear? Yes, sir. Yes, sir. Any problem in this? Yes. Okay. Very good. Now guys, you tell me, if I am donating 1 chocolate, how can someone have received 6 chocolates? Like for example, I have only one chocolate with me. But Dipin is saying to the world that Mrityunjay sir has given me 6 chocolates. So is it possible? I mean, is that chocolate magical? It will get multiplied by its own if I hand it over to Dipin? No. Clear सी बात है. It's normally clear to everyone that if Dipin is actually showing 6 chocolates to the classroom, then definitely I have given 6 chocolates to him. Now same thing is happening here. Iron is saying I am only releasing 1 electron. But chromium is saying to the world, no, we are accepting 6 electrons. See, that's the proof. 2 chromium here, 2 chromium here. We are accepting 6 electrons, which means there must be 6 electrons donated by iron. But as you can see, one iron can donate only 1 electron. Now guys, what to do? What to do? Yes. So here, in order to balance this out, we have to multiply this entire thing by 6. So therefore now chromiums are releasing 6 electron, which means there are 6 Fe positive, there are 6 Fe positive atoms or ions in the reaction. Now with this, we have actually balanced the iron atoms, chromium atoms and their electrons. So now let's rewrite everything properly. Let's rewrite everything properly. 6Fe dipositive Cr2O7 dinegative, giving us 6Fe tripositive plus 2Cr tripositive. Now guys, if everything is balanced here, the only thing remaining is oxygen. So now in the next step, let's balance oxygen atom. Now guys, on the reactant side, how many oxygen atoms you are observing?
7.
And on the product side?
0.
Okay. So the deficient side is product side. So the number of oxygen atoms present here, we have to add exactly the same number of water molecule. So if there are 7 oxygen there, I have to make 7 oxygens here. So I have to add 7 water molecule on the deficient side. So whenever you need to balance oxygen, add the required number of water molecule to the deficient side. Now see, oxygens are also balanced. Now the last and the most important thing, the reaction is actually taking place in the acidic medium and we have nowhere mentioned acid. So how we can mention acid? Just by writing H positive ions in the reaction. And as you can see here, everything is balanced, but on the product side there are 14 hydrogens, but on the reactant side there are 0 hydrogens. So now the final thing you have to do is just add the deficient amount of hydrogen ions on the deficient side, and with this your redox reaction is fully balanced. It is completely balanced now. Okay, now you have any doubt? You want me to explain this again, or any issues in any of the step, or is this thing is clear? Let's revise everything once again. What we'll be doing in the first step? Writing down the oxidation number. Second step, check which one is getting oxidized, which one is getting reduced. Step number 3, check the species is getting oxidized? It is getting oxidized by releasing how many electrons? If somebody is getting reduced, then it is getting reduced by accepting how many electrons? Also, by observing the number of electrons that are released or accepted, also check their number of atoms. Like we see in chromium, they are not balanced. So first balance that. Then accordingly write their electrons accepted and electrons donated. If they are not equal, make them equal. Like we did with iron. After doing that, when everything is balanced, balance the oxygen atoms by adding water molecule to the deficient site. Then in acidic medium, add H positive ions on the deficient side where hydrogen is less, and with this your reaction is balanced. Any doubt in this, guys?
No, sir.
No doubt? Okay. Now similarly, let's see one more reaction, but here this reaction is actually taking place in alkaline medium. So CrOH3 plus IO3 negative is giving us I negative plus CrO4 dinegative. Okay. Now guys, everything is similar up to balancing oxygen atom and hydrogen atom. So I would like you all to follow step number 1, writing down the oxidation number. Step number 2, check which one is getting oxidized, which one is getting reduced. Step number 3, balance their atoms and balance their electrons, which means equal number of electrons donated, equal number of electrons accepted. After doing that, we will proceed. So just try by your own. Yes, beta Anisha. Yes, they will clearly mention it to you that either the reaction is taking in alkaline medium or whether the reaction is taking place in acidic medium. Sometimes on the arrow they will give you H negative, OH negative ion, or sometimes on the arrow itself they will give you H positive ion. So with that you have to find out whether it is taking place in alkaline medium or acidic medium. Okay, let's see. So now tell me, what is the oxidation number of chromium here? Plus 3, because we know OH is a negative ion, so every OH have -1 charge on it. Okay, now what will be the oxidation number of iodine here? Very good, plus 5. Very good. What about iodine? Very good, superb. And what about chromium here? Plus 6. Okay, so now which one is getting oxidized, guys? Iodine is getting oxidized?
Oh, sorry, chromium.
Chromium, yes. Acha, chromium is getting oxidized. And by how many electrons? Chromium is getting oxidized by how many electrons? Very good. And what about iodine, guys? Okay. But by how many electrons? 6 electrons. Plus 5 tha, plus 4, plus 3, plus 2, plus 1, 0 and minus 1. So it is accepting 6 electrons. Now guys, is everything sorted or is there is something remaining? Now what we have to do? What will be the next step? What is still not balanced here? Okay. And why chromium is not seems to be balanced? I mean, why we are saying that chromium is not balanced? What is remaining?
There's plus 6 on one side and plus 3 on the other side.
Ah, so chromium is releasing 3 electrons, but iodine is taking 6 electrons. So now what we can do?
Multiply.
Yes, and multiply this chromium by what digit? 2. So we'll be getting 6 electrons. So 2 will be added here, 2 will be added here. So now guys, up to this method, everything will be same, whether it is alkaline medium or whether it is basic medium. So just for your sake, let's rewrite everything. Plus IO3 negative plus I negative plus 2CrO4 di negative. Now guys, next step will be same. Let's balance oxygen atom. And guys, what rule I have taught you? I mean, what I have told you? Whenever somebody asks you, okay, so tell me the oxygen deficient side. You tell me what is the oxygen deficient side? Reactant or the product? Okay, and how many oxygens are less on the product side?
2.
2. Uh, 3 oxygen multiply by 2, 6. There are 6 oxygen atoms in CrOH3. Agreed?
Yes. Yes.
And 3 oxygens on IO3 negative. So in total 6 plus 3, 9. Here 4 2s are 8. 1 oxygen is deficient. 1 oxygen is deficient. So I will be writing 1 water molecule on this side. Done?
Yes.
Now
Yes.
what is remaining? Hydrogen atoms. Now in alkaline medium the rule is changed. Everything is same in acidic and basic medium. Now when it comes to balancing hydrogen, the rule is changed. And now what is that rule? Okay, before knowing that rule, please tell me the side where hydrogen atoms are deficient.
Reactant.
uh Reactant side or the product side? Better it should be product side. See, 3 2s are 6. There are 6 hydrogens and there are only 2 hydrogens. So how many hydrogens are deficient? 4. 4 hydrogens are deficient.
Yes, sir.
So just add that number of water molecule on the deficient side. But just the same number of, I mean on the deficient side, you are adding water molecule and the equal number of, please everybody, just 1 minute, after that you can write. Dipin, focus, don't write. See here. Okay, so equal number of OH negative ion should be written on the opposite side. The side where hydrogen atoms are more and the side where hydrogen atoms are deficient. So to the hydrogen deficient side, add the required number of water molecule and Turant, exactly at that moment of time, write down the exact number of OH negative ion on the opposite side. We don't care about oxygen, we don't care about hydrogen, we don't care about their deficiency or their excessness. We just care about writing OH negative opposite to the side of water we are adding. That's the rule which is changed in alkaline medium. In acidic medium, we were simply writing the H positive ion on the hydrogen deficient side and we are done. But in alkaline medium, we are writing the number of required hydrogen. So we just add the required number of water molecule to the hydrogen deficient side and exactly same number of OH negative ion on the opposite side, and that's it. And now you can check everything is balanced, even oxygen atoms are also balanced. Now what is quite annoying, that is water molecules that are written differently. So finally you can write it down like 4OH negative plus 2Cr OH3 plus IO3 negative plus I negative plus 2CrO4 di negative, 4 plus 1 5 water molecule, and that's how we can balance a redox reaction. Any doubt, any sawal in your mind? No? Okay, so now you want to practice some questions.
Yes, sir.
Okay, so let's see. You have Mg plus HNO3 giving you Mg NO3 whole twice plus N2O acidic medium. Okay, go for it. Arey why Himanshi, you are done with this? Very good. It's Mg. Tasneem, it's Mg. Oh, you are confused with Hg. No, 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 but that's magnesium, everyone. That's magnesium. But yeah, if that is Hg also, it doesn't make any difference. Okay, you want me to solve this? Let's check. Let's check whether you guys have done it correctly or not. Ah, yes, Nisha, correct. I said Mg, na? Right. Okay, chalo, let's see. So, oxidation number of magnesium. Come on, what is the oxidation number of magnesium? 0. Nitrogen plus 5. Here, magnesium's oxidation number plus 2. And what about this nitrogen? Plus 1. Okay. So this is making our picture very clear. This is making our picture very clear. Now, magnesium is getting what? Oxidized. And and by how many electrons?
2 electrons.
And nitrogen is getting by,
4 electrons.
but what is the problem?
We need 2 more.
Yes. Here there are 2 nitrogens. There is only 1 nitrogen. So we need to make it 2 nitrogen here. Now 1 nitrogen was plus 5. Now 1 nitrogen is plus 1, which means 1 nitrogen is accepting 4 electrons. 1 nitrogen is accepting 4 electrons. But now we have 2 nitrogens. So 4 plus 4 in total, these 2 nitrogens are combinedly accepting 8 electrons. But accepting 8 electrons but donating only 2. बहुत नाइंसाफी है. So now what to do? We need, yes, we need to multiply this by 4 so that we get 8 electrons. So 4 will be coming here, 4 will be coming here. Now if everything is balanced, let's check oxygen atoms. Which one is oxygen deficient side, guys? Is it? Reactant side is deficient?
Yes, sir.
And by by how many oxygen atom they are deficient?
19.
19. By, is it NO3 or NO2? Let me check. Yeah, that is NO3. Hmm. 4 oxygen, 4 oxygen, 2 nitrogen, 2 nitrogen. No, guys, there is one more thing left here. There is one more thing which we are missing. Before balancing oxygen, your nitrogen atoms are not yet balanced. Can you see this?
Yes, sir.
Right now we have just see oxidize and reduce. But what about this nitrogen? 8.
So 4 H atom.
Sorry?
Oh, sorry.
2 into 4. 8 nitrogens are still present here. So we need to balance that also. So now we have to write 4 Mg plus 2 4s are 8. Nitrogens are here. They are only 2. So we have to take 10 HNO3 here. Then 4 MgNO3 whole twice, then NO2. Now I can say my every single atom is balanced except oxygen. Except the oxygen, right? Now see which one is oxygen deficient side or which one is oxygen rich side.
So product is
Product side. And by how many oxygen they are lacking?
6.
6. No, it's 5. 3 10s are 30. 3 2s are 6. 6 4s are 24 plus 1 25. So 5 oxygens are deficient here. So I'll be writing 5 H2O in order to balance the oxygen atom. Now oxygen atom are balanced. Let's balance hydrogen because that is acidic medium. So which side is hydrogen deficient?
Hydrogens are balanced.
Yes, hydrogens are already balanced, which means now our chemical reaction is completely balanced. So now in this reaction what we learned that sometimes there is only single atom on the product side, but there are atoms of the same time present in two different substances. So it doesn't mean that you have balanced the nitrogen atom and balanced their electron. This nitrogen is also balanced. No, we just balance that first, and in the last, when every atom is balanced, then we balance oxygen and then we balance hydrogen. So this is what you have to remember. Chalo. So I hope you got to know this method. Now guys, let me teach you the second method to balance the redox reactions are ion exchange method. Not ion exchange, I'm sorry, ion electrons है क्या लिख रहा हूँ मैं. आयन एक्सचेंज तो दूसरे चैप्टर में. आयन इलेक्ट्रॉन मेथड और हाफ रिएक्शन मेथड. Now guys, see, there is no difference in this reaction. There is no difference in this reaction. Let's write the same reaction again. Fe dipositive plus Cr2O7 dinegative giving you Fe plus 3 and Cr plus 3 in acidic medium. Guys, as usual, rule number 1, write down the oxidation number of each and every ion. Then step number 2, find out which one is getting oxidized and by how many electrons. Then see which one is getting reduced and again by how many electrons. So here there are 2, here there are 1. So 2, 3 2 are 6, 6 electrons. Now once this is done, step number 3 is different, guys. Please understand. Step number 3 is different. We will be splitting the reaction in two halves. First half is your oxidation half, and second half is your reduction half. So now in oxidation half, we'll be writing only those species that are getting oxidized. And on the reduction half, we are writing those species that are getting reduced. But we also mention their number of electrons. As you can see here, iron is releasing one electron. So I'll be writing that on the product side because iron is releasing, and because chromium is accepting, I am writing that on the reactant side. Now once this is done, again our every step will be same. What? As you can see here, chromium needs 6 electrons, but iron is releasing only 1 electron. So now in the next step, we will multiply this entire reaction by 6. So I'll be getting 6 Fe di positive, 6 Fe tri positive plus 6 electrons. Now I will balance oxygen and hydrogen atom respectively. I will just balance everything separately. But in iron, I cannot see any oxygen, I cannot see any hydrogen. Leave it. Now, reduction half, I can see 7 oxygen on the reactant side, but 0 oxygen on the product side. So I'll be adding 7 water molecule here. Oxygens are balanced, but the reaction is taking place in acidic medium. So now the hydrogen atoms, there are 14 hydrogen, there are 0 hydrogen. So I'll be adding 7 to the 14 H positive ion on the reduction half side. Now everything is balanced, but see, there is one problem. There is one important thing. Here 6 electrons are on the product side, and here 6 electrons are on the reactant side. So cut these electrons with each other. That is why it is balanced. Now just combine both reactions. Now combine reduction half and oxidation half. So it will be looking like Fe di positive plus Cr2O7 di negative plus 14 H positive ions, giving you Fe tri positive plus 2Cr tri positive plus 7 H2O, and your reaction is balanced. Easy हो गया? After learning the first thing, the second method becomes automatically very easy for us. Done?
Yes.
Which means the only extra step we are doing here is dividing the reaction in two halves and balancing each half individually. Like we balance this half first, then we balance this half first, then we add it all together. If there are some common ions, we will cut that. Like here there were 6 electrons on the product, 6 electrons on the reactant, we just cancel that with each other. If either they will be on the same side, like for example, just imagine there are 4 H2O on the product side and there are 7 H2O on the reactant product side. So 7 plus 4, 11. So here we will be writing 11 water molecule all together. Or maybe sometimes you will see 4 water molecules here on the reactant side and 7 water molecule on the product side. So we will subtract that because they are on the opposite side. So 4 minus 7, 3. So we will be writing 3 water molecules here. So that is the thing which you have to do. Now let's see one more example, that is Cl2 is getting converted into Cl negative plus ClO3 negative है क्या? Yes, that is a very common question, याद ही हो गया है अब तो मुझे. But this is taking place in alkaline medium. Now solve it by yourself. Try it guys by ion electron method. Split everything in two half. Then try to solve it.
Sir, for splitting into the oxidation of metals, we are taking one chlorine for each, right?
Yes.
Like one is getting reduced.
Yeah. You can see chlorine is getting reduced and chlorine is getting oxidized. That is disproportionation reaction. So you have to add Cl2. I mean, you have to take Cl2 on the reduction side also and on the oxidation side also. Oh, Faizan, you missed a lot. I will request you to please see the recordings, okay? Because you missed a very important thing. We have started balancing the redox reaction by ion exchange, ion electron method. Himanshi beta, if I can see your answer, 3 to the 6. There are 6 chlorines on the reactant side, but there is only one chlorine on the product side and 5 Cl is there. 5 Cl negative. Achha, okay. Yeah. Okay, no, just wait. Then 3, 3, 6, 6 on this side. H, 6, H, 6. Yes. It seems to be balanced. Yes. Very good. Okay. Let's try. Let's see everyone. Let's see. Oxidation number of chlorine on the product side 0. -1 plus 5. So this chlorine is getting reduced by 1 electron. No. I have to make this 2 chlorine. Multiply that by 2. So 2 electrons. And the same chlorine is getting oxidized by 5 electrons, but no, this is also 2 chlorines, so I have to make it 2, so 10 electrons. So now this is done, oxidation and reduction. Okay, now let's write oxidation half, Cl2 giving you 2Cl O3 negative. They are getting oxidized by 10 electrons, which means I have to write 10 electrons here. Now let's write reduction half, Cl2 is getting reduced into 2Cl negative by accepting 2 electrons. Now everything is clear, but this 2 electrons is not equal to 10 electrons. Here there are 10 electrons releasing, but they are accepting only 2 electrons, so I have to multiply this side by 5. So I'll be getting 5 Cl2 plus 10 electrons giving you 10 Cl negative, which means this 10 electron and 10 electrons are cancelled. Now what is left? Oxygen atom ko balance karna. So here there are 3 2s are 6. So we have 6 water molecules on the product side. 6 oxygen atoms, sorry. 6 oxygen atoms. So I'll be having 6 water molecules on the reactant side. Now there are 12 hydrogen atoms here and 0 hydrogen atoms here. So I have to add 12 water molecules here and have to add 12 OH negative ions here. Now let's combine everything. Let's combine everything. So guys, can I say that on the reactant side 6 water molecule will be cancelling this 12 water molecule, and now there are only 6 water molecules remaining. So finally we will be having Cl2 plus 5 Cl2. See, 1 Cl2 here, 5 Cl2 here, so total 6 Cl2 plus 12 OH negative giving you 2 ClO3 negative plus 10 Cl negative plus 6 H2O. So either you can write it down like this, or you can more simplify this by dividing each and everything by 2, because see, everything is getting divided by 2. So we will be getting 3 Cl2 plus 6 OH negative, ClO3 negative, 5 Cl negative, 3 H2. So very good, Himanshi. Very good, beta. You are getting the exact answer. That's really very nice.
Sir,
Yes.
sir, you can like separate the chlorine molecules, I mean the chlorine atoms for each half, and we'll still get the same answer, right? Because I did that for the same answer.
But the thing is, you cannot just separate Cl2. This is a molecule. Like for a reaction, for a sake of balancing, you cannot split a molecule in two half. What you did is, practically you have divided a molecule into two different atoms and putting that differently. So that is not the thing. You have to multiply that, which means one Cl2 is getting converted into Cl2 Cl negative. Imagine you have one chlorine molecule Cl2. The bond between that chlorine is broken and now they are divided into Cl negative, Cl negative. So that is the thing which is happening in reality. So you cannot do that. It will go against the rule of the chemistry. So that we cannot do.
Okay.
Okay guys, superb. So now we are done with balancing of the redox reactions. I know you guys require more practice and definitely we will do that. But let's get started with the new topic, that is a very small topic, that is redox reaction as the basis of titrations. Now guys, let me teach you what is a titration, or how many of you know what is titration? How many of you know what are titrations? Nobody knows this? Okay, Himanshi knows this. Very good. And other students don't know? Okay, so let me teach you. I have a plate. What is titration? Let's understand. Let's say I have a plate, and on the plate I have 12 slices of pizza. Okay? In a plate, I have 12 slices of pizza and I'm badly hungry right now. I'm full on hungry. I have not eaten anything and now I can test my capacity. So I took the first slice, खा गया. Second slice, gone. Third slice, gone. Fourth slice, gone. Fifth slice, gone. Sixth slice, gone. And now I am डकार आ गई. I burped, and you all know burping is the sign that now your stomach is full, you have to stop. So as soon as I burp, I am done. So what is this? This is titration. This is titration, which means my stomach is not stomach, is a conical flask and it having reactant B. It have reactant B whose concentration is unknown, because you all know how much pizza slices I can eat, you don't know right now. Similarly, the chemical which is filled in this conical flask, its concentration is unknown. Now the plate in which we know there are 12 pizza slices is your titrating funnel, is your titrating flask. It is a long cylindrical rod that have ml marked on it, 0 ml, 1 ml, 2 ml, 3 ml, 4 ml, 5 ml, 6 ml, it's like that. And in that you took the another reactant whose concentration is known because you have taken out its reading. In that you have taken 1 mole of the known reactant in that conical flask, which means its concentration is known to everyone. Similarly to the plate that have 12 pizza slices, which means you have 12 pizzas with you. Now you took the first pizza slice and put it in my stomach. गायब, खा गया मैं. सेकेंड स्लाइस भी खा गया, थर्ड भी खा गया, फोर्थ भी खा गया, फिफ्थ भी खा गया, और सिक्स खाने के बाद में डकार आ गया. दैट इज द एंड पॉइंट, which means the capacity of my stomach is 6 pizzas. My stomach is capable to digest 6 pizzas, and after consuming 6 pizza slice, burping is showing the end point. Similarly, you take that titrating flask, in that the concentration of your reactant is known. You have conical flask below to it, in that your reactant is there but its concentration is not known. Now you started the dropper, and drop by drop from the titrating flask, the chemical, the reactant with known concentration is, you know, it's getting drop, we are dropping that into the conical flask, drop by drop, drop by drop, drop by drop, drop by drop, drop by drop. But guys, you all know that the concentration of this chemical is not known and it is present in limited quantity, which means the reagent that we have taken in the titrating flask will not be fully consumed. Maybe from that from that titrating flask in which we have put in 100 ml of your reagent or the reactant, maybe 30 or 40 ml is consumed, because the conical flask have limited amount of reactant in it. So how we will be able to know that the reactant that is present in the conical flask is completely consumed? Because that is our limiting reagent, I hope you all know, which is present in lesser quantity. When it is completely consumed, which means when A and B fully reacts, the reaction will over. So how will we be able to know that reaction is over? We add a indicator to it. We add an indicator to the conical flask. So as soon as the extra drop of your reactant falls into conical flask, once the reaction is over, now there is no more reactant left in the conical flask, so as that can react with the substance that is present in the titration funnel. That indicator will turn its color, and that change in color will show that the reaction has reached its end point. And now, with the help of the remaining solvent or the reactant in the titration flask, you can find out the concentration of that which is present in the conical flask. Are you getting the principle of titration? So basically we have a chemical reaction going on, but in that we don't know the concentration of one of the reactant, and we take that in the conical flask. The concentration of the known reactant, we take that reactant in the titration flask. We do the titration, see the end point, and with the mathematical calculation we can find out that what was the amount of concentration or what was the concentration of solution was present in the conical flask. That's the principle of titration. Okay, yes, very good. Yeah, Nisha, very good, superb. So now redox reactions are very important for the titration. Why? Because in redox reactions, the indicator that we use, they will get oxidized or they will get reduced in order to show their effectiveness, in order to show their color. So basically, to detect the end point of the reaction, we need redox indicator, which means the indicators that we are using are actually redox indicator. They have capacity to oxidize or get reduced. Now let's talk about the first thing, that is self indicator. Self indicator means in the chemical reaction, one of your reactant is indicator also. Are you getting this point? Your reactant is indicator also. For example, permanganate ion, that is your KMnO4. Okay, so whenever you see Fe plus 2 reacting with MnO4 di-negative, you all know that here manganese have plus 7 charge on it. So you will see manganese is getting converted into plus 2 and iron is getting converted into plus 3. So what happened in this reaction? This manganese that was acting as your reactant and it was acting as your indicator also, itself get reduced to oxidized this iron. Are you getting this point? So now this manganese is your indicator. So we take this in titration flask because that is purple in color. We know that this is a violet or a purple color thing, and we take iron in the conical flask. We take iron in the conical flask, and in the titration flask we take MnO4 di-negative because right now that is purple in color. Now what will happen? When I just open this tap, one drop will go into the solution to book. And this iron is colorless. This iron is colorless. So as soon as this one drop will fall into Fe dye positive, we shake it, it again becomes colorless. Why? Because this MnO4 reacted with iron. So the product that we are getting is also colorless. So as soon as the color of MnO4 negative becomes colorless, we will say that reaction is going on, because this MnO4 is getting consumed by Fe dye positive. So this colorful MnO4 becomes colorless when it meets Fe dye positive. But after some time, when the entire Fe dye positive is consumed, when the entire Fe dye positive is consumed, what will happen? Now as soon as this extra drop of MnO4 negative falls into the conical flask, now there is no Fe dye positive left to react with that and makes it colorless. So now your solution will show violet to purple color. So now the solution that is present in the conical flask will not become colorless, and this shows your end point. And this shows your end point. Is it clear?
Yes, sir.
So this is used for Fe dye positive, CrO4 negative, so many things, and it is very applicable at very low concentrations also. So this is your self indicator. Now let's talk about some other redox indicator. Now guys, as you all know, these redox indicators, sometimes we can also use them as reactant also. That's not the point. See, chromate ion Cr2O7 dinegative, we have seen this reaction also. We have seen this reacting with Fe dye positive, right? We have seen some of the reactions right now only. So this is also a compound which is not actually a self indicator, but it gave color by oxidation. Why? Oxidizing the indicator after all the reductants are consumed, which means what will happen? See, now we will take this dichromate ion in the titration flask and the quantity of Fe dye positive in the conical flask limited. Now what will happen? In this, see, again in the conical flask we have Fe dye positive. In the titration flask we have Cr2O7 dinegative. But you know what we did? We added some indicators to it. And what are these indicators? Diphenylamine. We added diphenylamine to this Fe dye positive. Now what will happen? When this drop of Cr2H7 falls in the Fe2 plus Fe dye positive, there will be no color observed. No color. Why? Because Cr2O7 is reacting with Fe dye positive. But once this entire Fe dye positive is consumed, there is only indicator which is left in the solution. And now that excess drop of Cr2O7 will go and find Fe dye positive. But that is nowhere, it is already consumed. So now it will react with diphenylamine. This Cr2O7 will oxidize this diphenylamine, and this will start showing its violet color in the solution. So now when your solution becomes green or violet, you will see your end point is achieved. So here Cr2O7, which is one of your reactant, is not your indicator. So in order to show the end point, we need an extra indicator to be added in the conical flask. Similarly guys, we have iodide indicators also. So iodide, when oxidized by oxidants such as Cu dye positive, this iodine is formed. As you can see here, if I have some iodides with me and I have some oxidants, that is Cu2 positive, here you will see Cu2 is getting +1 charge and iodine is getting 0 charge, which means iodine is getting oxidized. And now once this iodine is formed, you know what we do is, this iodine is actually insoluble in water. So its solution is prepared in water containing small amount of potassium iodide, in which iodine dissolves to form water soluble Ki3. Now by adding a pinch of starch, it gives a deep blue color which shows the end point. So what we do is, the solution that we are making in the conical flask, in that we add water, but along with water we add Ki also, potassium iodide also. So when during the chemical reaction, when this iodine is formed, it is actually insoluble in water, so you will see the layer of iodine, but we don't want it, so we add water plus potassium iodide in the beaker. Now this iodine is formed, and because of Ki it becomes soluble in that solvent. Now we add a small amount of starch to it, and we keep on doing the reaction. As soon as this excess amount of iodine is formed, this iodine will start reacting with the starch that was present in the solution and will give you deep blue color that shows the end point of the reactant, the end point of the reaction. So here what we do is, the conical flask that we are taking, in which we have Cu dipositive ion, in that we added water, we added potassium iodide, and we added starch. And in the titration flask we take this iodide ions. Now iodide ion will go this, will consume the entire Cu dipositive. Now as soon as iodine will form, it will react, it will dissolve in water and Ki, and will react with starch to give you blue color, and that will show your end point. So guys, this is how titration works. This is your iodide indicators. Now let's see some of the important terminologies. Guys, titrant. Titrant is something whose concentration is unknown, which is kept in the conical flask below. Titrant, whose concentration is known, which is kept in the titration flask. Endpoint, it is the situation where your reaction is over or your titrant is consumed completely. An equivalent point, a point at which both reductant and oxidant are equal in concentration, which means both of your reactants, one is getting reduced and one is getting oxidized. So when both of them are present in equal quantity, we will call it as equivalent point. We will call it as equivalent point. So these are the some basic terminologies of the redox reactions. And redox reactions and electrode potential, that we'll be discussing in the next class. And yes, with this guys, our today's lecture is over. We are done with today's agenda. Now when we'll be meeting in the next class, I will teach you a very important cell, a very important concept that will be used in class 12th also. Okay, so with that, that thing maybe require around 45 minutes, and in the remaining 45 minutes we will practice some of the questions from balancing. So today just revise the concept, see the titration thing, and in the next lecture positively we will be ending up this chapter. So this chapter is of only one more lecture, and we will not be require any boosters to practice this chapter, because you know balancing of redox reaction is clear with you all. But yes, definitely in the boosters we will definitely take some of the questions from this chapter also, and with this we will be starting up with the thermodynamics after the next class. Okay, so this chapter number 5 will get over in the next lecture. Okay.
Okay, sir.
Okay, so I hope everything is clear with today's lecture. There is no doubt in today's lecture.
No, sir.
Okay, so just go through everything, and if you feel so that you are having any doubt, you can ask me in the next class. Okay, chaliye, so then bye bye everyone. Let's end the session for today. Thank you so much for joining. Good night everyone. Take care. Sweet dreams. Bye bye.
Bye, sir. Thanks.
Bye. Good night. Good night everyone. Good night. Thank you so much for joining. Bye bye. Okay, you have physics class left after this, and the duration of physics class is 2 hours, right?
Yeah, like 1 hour 45 minutes.
My god. Okay, chalo, so all the best for your physics class. And today we don't have any class, so today we'll be getting a bit relaxation. Today I am not available, so you guys have an off today for chemistry. Chalo, bye bye, good night. Thank you so much for joining. Take care. Sweet dreams.